Good afternoon, everyone. Welcome to NET310, a session where we explore best practices for building networks for growth and flexibility. My name is Sid. I'm a principal solutions architect with AWS, and I'm joined today by Ben. Ben is a principal network engineer with Sonos, and towards the end of this presentation, he'll come on stage and share his journey and how Sonos built networks on AWS for growth and scale. Now, every organization is on their journey of cloud adoption. Either you're migrating your applications to the cloud or you're building net new applications, hopefully now with generative AI. One thing is certain, the number of applications will keep growing. So we as network engineers, network architects, need to build networks that can scale and can adapt to any kinds of applications and their requirements. That is the theme of this session on how we do that. Now, networking and scale are multifaceted. So let's look at a few examples. Let's say you have an application which has really high throughput requirements. For that, you need to think about, hey, is my EC2 instance the right type? Can it fulfill the network requirements? What about my load balancing? Okay, how do I shard traffic across different load balancers and instances? Next challenge comes from having a large number of applications with different networking requirements, some internal, some external. You think about how can you isolate these applications from each other or connect them together if needed? How do you enforce security? Next, you might have a large number of business units, and you might want to isolate these business units into their own routing boundaries. You might want to do layer 7 inspection. And finally, given the global landscape we live in, we are all building global networks. And here, you want to set up optimal global routing, unified security operations, and a single pane to manage all of that. Now, in today's session, we'll focus on the bottom 3 challenges, which has more to do with network connectivity at scale. Now, if you have not seen those scale challenges before, don't worry. Hopefully, you can learn and evolve from where you are today. Let's go back to the age of dawn, when all we were tasked to do was manage and operate our data centers. You could walk down your data centers, you could physically touch the switches, cables, fun times. And then came the cloud, AWS. Initially, you thought of cloud as a way to deploy your backups, disaster recovery workloads, but that quickly changed. And now you started deploying production applications, critical applications, and you had requirements to connect your remote offices, your branch offices, your on-premise infrastructure to the cloud infrastructure directly for low latency, high throughput. And it quickly became a mess of mesh, as I like to call it. A better approach is to have AWS in the center, act as a brain, and leverage AWS global backbone with AWS software-defined service on top to manage routing between all of your infrastructure, whether it's cloud infrastructure or on-prem. And this is the approach which we'll be talking about in this presentation, and it promotes simplicity as well as scale. Now, as we compare and contrast different options to achieve that design, we will use the AWS well-architected framework to compare and contrast different options. All right, let's get into it. How do we architect for growth, scale, and flexibility? The answer, my favorite one, is it depends. It depends on your application's networking requirements. So let's start there. First, we focus on what's your application's traffic paths. Is your application and all its dependencies confined within a VPC, or is it spread across? Let's take a step back. Should you put all of your VPC and infrastructure into a single VPC, or should you split it up across VPCs? A very fundamental question. How many VPCs should you have? For scale and growth, you need to get this right. I've seen a lot of customers who get this wrong and then have a lot of scale challenges. Now, VPC, I look at it as an ideal network isolation boundary, something which limits scope of impact. So often I see customers take a strategy where a VPC translates to an application network boundary, so you deploy different applications in different VPCs, or it can also translate to environments, so prod, non-prod, dev, test VPCs. You can go as granular as having a VPC for every microservice of an application, or take a more macro approach where you are bundling different applications of a lines of business in a VPC. What is the right approach, you ask? It depends. There's a lot of factors which you need to consider. But one thing which people often miss is the people process aspect. If you're an organization which is distributed in manner, you have two pizza teams who own and manage the entirety of an application, all the way from security to operations to networking, then it makes sense for you to have a more distributed approach where you have different VPCs and accounts per application, or even microservices, depending upon the size of the applications. One thing is certain, don't go extreme. Don't build one VPC, don't build 10,000 VPCs. Find an approach which works for you, and you're somewhere in between. Another important question is, how large can a VPC be? It is not a it depends kind of an answer. It's a factual answer. And you can measure the size of a VPC using a metric called NAU, or network address usage. Now, as the name suggests, it's how many addresses you use in a VPC. But it's not that straightforward. Let's look at an example. NAU is 1 per every IP address assigned to an ENI. It's also 1 per prefix assigned to an ENI. So you can assign a /28, for example, to an ENI. But it is 6 for AWS managed ENIs backed by Hyperplane. So when you're using VPC endpoints, Lambda functions, NAT gateway, services like that. The quota is 256,000 for a VPC, or 512,000 for a VPC which is paired with other VPCs. Use Amazon CloudWatch to monitor the NAU of your VPC. Now, one strategy of building networks on AWS, which often leads to creating really large VPCs, is VPC sharing. With VPC sharing, the idea is you assign individual accounts to different application components, but from a networking standpoint, all of them are deployed in a single VPC. So you're sharing a single VPC with different accounts. Now, you would want to do that because you want the different components of your applications to be co-located as close to each other. It reduces latency, and as well as reduces your data transfer charges. It also promotes segregation of duties, where a central team manages the VPC, and your application owners don't have to worry about it. But again, be careful of building really large VPCs. NAU limits apply, but also managing security groups, network ACLs, and of course, the scope of impact is high in that case. One reference architecture I can share on how you can go about creating shared VPCs is a strategy where you're bundling different lines of businesses into a VPC. So you create a shared VPC for, let's say, marketing apps, and then share individual subnets with different application owners within that line of business. Another approach is to have a VPC for a really large platform which has a lot of microservices, and then share those VPCs with individual account owners who owns those microservices. Whatever the strategy you go with, one thing is certain, you'll have multiple VPCs, and you will have a need to connect them. So let's jump into how do you connect VPCs at scale. Now, we have Transit Gateway Cloud WAN. Which option do we go with? Before we make a decision, we need to go back to our application's requirements. Do they need cross-region access? Do they need on-prem connectivity? What are their security requirements? Do they need segmentation, deep packet inspection, zero trust? What is their bandwidth and latency requirements? And cost is important, so understanding how much data transfer will happen between the application components. So let's look at our first option, which is Transit Gateway. Now, Transit Gateway promotes scale by building a hub-and-spoke design. You have a transit gateway which can connect to up to 5,000 network attachments. It supports global connectivity, so you can deploy a transit gateway in every region, and you can connect or peer them together through Transit Gateway cross-region peering. Now, keep in mind, Transit Gateway is a regional service, so you will have to go to each and every region and configure the Transit Gateway, so regional operations. It also promotes hybrid scale. We recently updated the quotas for what you're going to see next. So you can connect your Direct Connect gateway to up to 6 transit gateways, and you can create 4 transit WIFs per Direct Connect connection. In essence, over a Direct Connect connection, you can connect up to 24 transit gateways if you do the simple math here. Also, from Transit Gateway, you can advertise 200 prefixes down to your on-premises routers. Now, keep in mind that you have to write static routes to do so. So you can see the screenshot here. You can see the section allowed prefixes. That is where you would enter those prefixes. Also, when you're setting up cross-region transit gateway peering, you have to write static routes. And you can see an example of that in the screenshot below. Now, from a security standpoint, you can create regional segmentation using route tables. Here we have prod, dev, and peering route tables, and then we can associate our attachments to these route tables. You can have 100+ route tables, and a very common question I get is, how many route tables should I have? You know the answer, it depends. But the way you can approach it is, route table should be a superset of your VPC design. So if you have multiple VPCs, which are production VPCs, then you can create production segments like I've done here. Maybe you can create route tables for your lines of business, if that is how you have segmented your VPCs. Right? So it is a subset of your VPC design. That's why getting VPC design is quite important. Keep in mind, segments don't extend globally, so you cannot say, hey, my prod wants to talk to prod, my dev wants to talk to dev across regions. You cannot peer them. You can also set up layer 7 security, so you can add an inspection VPC with network firewall or gateway load balancer and write routing logic saying, hey, if my traffic is crossing prod and dev boundaries, then it should flow via the inspection VPC. Performance standpoint, 100 gigabits per second per attachment per AZ. And from a cost standpoint, data processing charge and an hourly charge. Now, if you look at all of these well-architected pillars here, you can see from an operational standpoint, you still have to write static routes. And it has regional operations. Also, segments don't extend globally. So you can see there is some limitation when it comes to building global networks. And that's where my next option comes in, AWS Cloud WAN. So here, we are building global networks using this service. In this architecture, you have your on-premises setup. You bring in AWS regions, start migrating workloads, and you build a mess of mesh. So we want to solve that. We build a global resilient routing layer using AWS Backbone. Cloud WAN comes on top of it. So with Cloud WAN, you provision CNEs, or Cloud Network Edges. These are regional endpoints fully managed by AWS. All of the CNEs are fully meshed together, and there is dynamic routing between them. You connect your networks to the nearest CNE. You can connect your remote offices via SD-WAN connectivity as well, something which we'll dive into later. Once you do all of that, the CNEs will exchange routes globally. You don't have to write any static routes. It's all dynamic routing. You can connect up to thousands of networks, with 5,000 being the default quota. You get the hub and spoke design. You get dynamic routing, and you get global pane of glass. So using the AWS Network Manager dashboard, you get a rich visualization of your network. You can drill down into your network topologies. You get different topological maps, as well as visibility into all the events within your network. So if BGP goes up, BGP goes down, for your SD-WAN connectivity, for example, you'll see all of that in one central location. OK, a slightly different visual, but the same thing. We have our Cloud WAN core network in between. On the bottom is the on-premises infrastructure. On the top are your VPCs spread across 3 AWS regions. You create attachments, attaching your VPC to the nearest CNEs. From on-prem, you can create IPsec site-to-site VPN. For SD-WAN connectivity, you will provision an SD-WAN appliance in a VPC, connect that VPC to the CNE using VPC attachment, and then over top of that, you create what's called a connect attachment. Through a connect attachment, you can create a GRE tunnel between Cloud WAN core network edge and your SD-WAN appliance and run BGP over it to exchange routes and traffic. Now, this is how you used to do things until a few weeks back, where we released Tunnel-less Connect. Let's dive into what Tunnel-less Connect is. Our overall goal remains same. We want to connect SD-WAN appliances in a highly available manner to Cloud WAN core network edge. First, create VPC attachment, which deploys Cloud WAN ENIs into your transport VPC. Next, we create Tunnel-less Connect. This provisions two IPv4 addresses for BGP peering. These IP addresses are now accessible via the Cloud WAN ENIs, which get deployed in your VPC. So you go ahead and provision the BGP peering relationship between these IPs and your SD-WAN appliance, and that's it. That's all you have to do. No GRE tunnels required. We have a bunch of partners who are already supporting tunnel-less connectivity today. How does it change things for you, though? Well, with the tunnel-based connect, where you're using GRE, you could only get 5 gigabits per second per GRE tunnel. But now, With tunnelless connect, you get 100 gigabits per availability zone. That's huge. That's a huge difference. There are some architectural considerations which you should keep in mind. Only one tunnelless connect attachment per VPC, and the transport VPC attachment and connect attachment should be associated with the same segment. Now, if these don't make sense to you, don't worry. Later on in the presentation, we'll talk about some architectures where we'll use these considerations. Also, a best practice, run your SD-WAN appliance in the same subnet as your transport VPC attachment. That is exactly how it's shown in this diagram. Now, why should I do that, you ask? Well, if you don't do that, you'll have to write a lot of static routes to make it work, which we don't want to. There's a blog with this QR code where it talks about more details on how you go ahead and do all of that, some of the best practices, considerations, etc. All right, continuing on. When we want to connect our on-premises infrastructure to Cloud WAN, we have to do it via Transit Gateway. So Cloud WAN today does not support native Direct Connect attachment. The routes you advertise from on-prem up towards Transit Gateway and up towards Cloud WAN is all learned dynamically, but you still have to write those static routes from Transit Gateway to Direct Connect. Next is a feature which I really like about Cloud WAN is the network policy. So you can define your entire Cloud WAN configuration through a JSON network policy. Here's an example of a policy. You specify the edge locations where you want to deploy your global network into. So here, US East 1, US West 2. You define your segments. You define segment actions, which basically say share routes between certain segments. You can also write static routes here. And finally, you can write attachment policies which automate how your attachments get associated to certain segments. And here it's done based on tags. You get policy versioning, so you can deploy different policies and it gets versioned, and you have also the option of rolling back to a previous policy. Now, when you create a policy, Cloud WAN allows you to validate the policy by creating a change set. You get to see exactly what's changing in your policy. You validate that, and then you execute it. And when you execute it, it makes changes to your Cloud WAN network globally. So no more going to a regional console and making changes. It's all global operations. Now, you would want to integrate this validation step, this change set validation, into your net DevOps pipelines. Don't know what DevOps pipelines are. It's the practice where you would take DevOps principles and adapt them for making network configuration changes. This is another one of those practices which you must adopt if you want to grow and scale from a networking standpoint. Treat network configuration as code, very similar to how we do it with Cloud WAN JSON policy documents. Store them in a version control system. Use CI/CD to implement and test changes on your networks. Here's an example of how you do that, end to end. So scenario here is we have a networking account with Cloud WAN in it, and we want to automate provisioning of new VPCs and attaching the VPC to our Cloud WAN network. Through a self-service portal, you let your application teams define what they want. Now, they can do this through service catalog or a custom UI, doesn't matter. They are entering, hey, I need a VPC, it's a dev VPC, I need a /24, etc. Based on that, a CloudFormation template or a CDK script or Terraform, whatever, gets generated. That triggers a CI/CD pipeline. A key step here is to have automated network configuration checks. You can check a whole lot of things. You can check, for example, the application team requested a dev VPC, and they also requested an internet gateway, but you don't allow that. Your policy denies that. So you can go ahead and fail the pipeline. Right? So there are a bunch of guardrails you can put in there. Once that's all validated and everything is good, it goes ahead and creates a VPC, creates an attachment, and tags it. From here, you can add a human approval step. So someone will go into the Cloud WAN console and see, hey, somebody requested attachment connection to my dev segment. Should I allow it? Yes. And then the Cloud WAN automation kicks in. It will map the attachment to the right segment, learn all the routes, propagate all the routes. Everything happens dynamically. Finally, you go ahead and test your connectivity within your VPC. Everything's fine. You end your pipeline. OK, coming back to our Cloud WAN. From a security standpoint, you can create global segments, very similar to how you do it in Transit Gateway, but these are global segments, so they are consistent across AWS regions. You associate your attachments to the appropriate segments. Now, for associating Transit Gateway to Cloud WAN segment, it's a bit more nuanced. So let's see how that works. So within Transit Gateway, you have route tables. When you want to associate that to Cloud WAN, you can actually associate individual route tables to Cloud WAN segments. So in this case, I'll take the hybrid route table in my Transit Gateway and associate it with the hybrid segment of Cloud WAN. You can also build layer 7 security with centralized inspection. Works very similar to how Transit Gateway works, but here again, it's a global segment. You would deploy centralized VPCs in each and every region. These will have your NAT gateways, your network firewalls, all kinds of shared resources. Now, if you want to dive deeper into how you configure network inspection and how you do all of the routing, et cetera, because you do have to write some static routes, you might have to create additional segments based on what you're doing. There's a good blog to learn about it. But today, what I want to focus is on the fact that traffic inspection should be done thoughtfully. Every time, let's assume that you are inspecting traffic between regions and across segments. You will have to you add 4 additional hops to do that. You process the data twice additionally to do it. And you don't want to do that for all traffic. So how do you go about doing this? So the inspection strategy, one is inspect everything everywhere, across segments, within region, across region, on-prem, left, right, east, west, everything. If you do that, to make sure that you're not going crazy on your latency and data processing charges, your VPC design is key. You want to make sure that your application components, because you typically inspect between VPCs, not within VPC. So you don't want to deploy application components across VPCs when you want low latency access and you want to keep your data transfer costs low. What I prefer and I advise is inspect between security zones and boundaries. Typically, you map your Cloud WAN segments to security boundaries and then inspect between segments. So if the traffic flows between dev and prod, then you inspect it. But if the traffic is within your prod segment or within your dev segment, don't inspect it. All right, from a performance standpoint, up to 100 gigabits per second per attachment per AZ, very similar to Transit Gateway. And cost, data processing charge, and per attachment charge, very similar to Transit Gateway. Now, if you're thinking, why does it sound everything so familiar to Transit Gateway? It is because we are using a similar technology as Transit Gateway underneath. But Cloud WAN provides you with this rich automation and dynamic routing. OK, so those was Transit Gateway and Cloud WAN. Now, I want to talk about some purpose-built VPC connectivity options. The first one is VPC peering. Now, VPC peering was the first connectivity model we ever released. But now it has taken the role of a purpose-built model. When would you use VPC peering? It does not scale. It is not very operationally excellent. Security, just layer 4, no layer 7. So why would you use it? Because of performance. When you peer to VPCs, there is no gateway in between. If you peer to VPCs and the EC2 instances within those VPCs belong to the same AZ, there is no data transfer charge. So if you have applications across VPCs which you want to connect, and they are very chatty and just transferring gigabytes or petabytes of data between them, you want to be mindful of your data transfer charges, and you want to use VPC peering. Next purpose-built option is private link. This is where you have a service as a service provider, and you want to share it with multiple consumers. But you don't want to expose your entire VPC and your entire network. You want to only expose a certain service. So with this model, the service provider would create an endpoint service and share it with the consumer accounts. The consumer accounts would create an interface endpoint to that endpoint service. Behind the scenes, a private link connection gets created. There is no VPC peering, there is no Transit Gateway, there is no Cloud WAN. This is a different data plane. From a scalability standpoint, service provider gets unlimited scalability, and you have 100 endpoints per VPC for service consumer. Fully managed. From a security standpoint, it's just one-way connection. The service provider cannot initiate a connection back to consumer. You can use security groups. And if you're using private link to access AWS services, which is a supported model, you can also write endpoint policies, which are finer grained policies. Performance standpoint, it automatically scales up to 100 gigabits per second. Again, pay as you use, hourly charge, and a data transfer charge. The next purpose-built service is VPC Lattice. VPC Lattice is the epitome of a fully managed networking service. This is where you, as an application owner, would want a fully managed service with built-in authentication, built-in monitoring, built-in traffic shaping, built-in service discovery and health checks, but without sidecars, without any agents. All of this functionality fully managed, built into the VPC's data plane via Amazon VPC Lattice service. So you would create a service network and register your microservices, which can be in different accounts, in different VPCs, as services as part of the service network. When you do so, these services can communicate with each other with all of that functionality through the VPC Lattice data plane. This functionality works homogeneously. So you can have EC2 instance in one VPC and a Lambda function in another VPC, or EKS, or ALB, and it can connect all of that together. You get zero trust. Every packet is authenticated and authorized using IAM. 100 gigabits per service per AZ is the performance, and there are 3 metrics here from a cost standpoint. Again, very pay-as-you-go kind of a pricing model. All right, so which option should I use? Choose a default connectivity model and build and add on purpose-built connectivity based on use cases. I recommend, if you have any kind of global presence, use AWS Cloud WAN. So let's do a group exercise here. Let's see how we can combine all of these connectivity models together. So I have 2 VPCs. 1, 2, 3, 4, 5, 6 are my EC2 instances. I also have some containers with 2 subnets. I'm going to start first. I'm going to choose a default connectivity model, and that will be Cloud WAN. So I'll connect these VPCs through core network edge because they're in the same region. Next, an application team comes in and says, I have a requirement. EC2 instance 3 and 4 needs very high throughput connectivity to instance 1 and 2. They are in the same AZ and would like to keep data transfer cost to a minimum. This, by the way, sounds like a network certification exam question. It might be. So what connectivity model would you choose here? Would you stick with core network edge like Cloud WAN, or would you bring some other connectivity model? Anybody? You can shout out. VPC peering. Amazing. So we create VPC peering. And the way we route traffic via VPC peering is by creating a more specific route in the VPC's route table. Next application team comes and says, hey, I have an EKS cluster in 2 VPCs. They want to communicate with zero trust IAM policy authentication. I also need service discovery. What do I go with? VPC Lattice. Amazing. Now, how does this work? When the services do service discovery, they are going to get a URL name, and the URL translates to a link local IP. So the traffic goes and gets ingested into the hypervisor through this link local IP into the VPC's data plane. It never goes to Cloud WAN. Final requirement, app team just purchased a third-party SaaS product, need private one-way connectivity. What do? Private link. Here, we go ahead and provision a private link. Again, DNS translates the private link endpoint service. DNS translates to the interface endpoint, which is within the VPC, so it never goes to Cloud WAN. For everything else, there's Cloud WAN. So my default route points towards my core network. OK, awesome. Some other scale considerations. IP addressing. Another one of those fundamental things you need to get right. I have met so many customers who have overlapping CIDR addresses, who are running out of IP addresses, and it's not pretty at all. So you want to make sure that you choose an IP addressing design where you can summarize IP ranges from an hierarchical standpoint. You pick and choose your hierarchy, but typically assign ranges to different regions, and within those regions, assign ranges to different environments, maybe different lines of business, maybe application groups. You pick and choose, but summarization will be key. Makes writing static routes easy, makes firewall entries much easier as well. We have a service, VPC IP Address Manager, which helps you do IP address management in the cloud. So if you're not using that, that's something which I recommend using. We recently made changes to how we price IPv4 public IPs. So you can use IPAM public IP insights to figure out what that IPv4 address usage is from a public standpoint. Finally, if you have not looked at IPv6, you should, especially at scale, because as you start building VPCs, thousands of them, and you have these massive container workloads, generative AI applications coming in, there will be a moment where you'll run out of IP addresses, and IPv6 will be your only option. So think of it early on. Next consideration is about centralized and distributed architectures. This is where you would centralize certain services, for example, firewalls, NAT gateways for centralized internet egress. Which one should you go with? Any one. Standardize on an approach. I've seen most customers standardize on a centralized approach, but then enforce repeatable and guardrail patterns for exceptions. I'll give you an example. An application team comes in and says, I'm deploying a customer-facing, public-facing application. Centralizing internet ingress is very difficult. Centralizing internet egress is much easier. So having a distributed internet egress model makes much more sense. But you don't want to just go and tell the app team, hey, you can just go and deploy internet gateway in your VPC and accept traffic. No. You want to make it repeatable using NetDevOps. Create a NetDevOps pipeline. An example here would be to deploy an ALB with a WAF on top of it, and you can use AWS Firewall Manager to manage WAF rules across hundreds of ALBs and different accounts within your organization. Right? So it's this distributed model, but you still have centralized control. And you're making sure that they are deploying based on the best practices and guardrails you have defined within your NetDevOps pipelines. All right. So let's look at some more best practices. And here we will run through some sample architectures and some advanced scenarios. So I have hundreds of VPCs across multiple regions, and I also have on-premises connectivity, but I'm using Transit Gateway. I want to move to Cloud WAN to enable further scale. So here's my architecture where I have 2 transit gateways with 3 route tables across 2 regions, and I also have on-premises connectivity via Direct Connect. I go ahead and provision AWS Cloud WAN. I start by mimicking the route table design of my transit gateways into the segments of Cloud WAN. Now I go ahead and associate the segments between transit gateway and Cloud WAN. Now, what this does is sets up dynamic routing between transit gateway and Cloud WAN. You essentially, what you have done is you have enabled dynamic routing between the transit gateways, because the 2 CNEs of Cloud WAN will learn the routes from transit gateways and advertise them across each other, across regions. You have essentially peered prod and prod, dev and hybrid across regions of 2 transit gateways. You could not do that with VPC pairing, but you can do that by putting Cloud WAN in between. This is a good starting place if you have not used Cloud WAN before. Once you do this, set this up, next you can go ahead and attach your test or dev VPCs to Cloud WAN. In the dev VPC route table, you'll have to make a route table change. So instead of pointing it to transit gateway, you point it to core network. Now you verify the network connectivity, make sure everything's working fine, and then deattach the dev VPC from transit gateway. It's done. Now all you need to do is repeat it 1,000 times for all your VPCs. But you have to do it using NetDevOps pipeline, right? So it happens automatically with built-in validation and testing. OK, so we have successfully migrated to Cloud WAN, and I have 2 regions here. Let's look at our prod segments route table. I'm looking at a global route table here. You can see all my prod VPCs are in the route table, so my prod VPCs can talk to each other. I also have routes for my on-premises network through Transit Gateway A and Transit Gateway B. Now, if the traffic initiates in region 1, it is going to flow down via Transit Gateway A. And if the traffic originates in region 2, it is going to flow down via Transit Gateway B. Why does this happen? That is because there is CNEs in those regions which are making local routing decisions. And these routing decisions are made based on Cloud WAN route priority. This is a screenshot from our documentation. If you see point number 2, for routes with same destination IP addresses but different next hops, static routes are preferred. VPC propagated routes are preferred, and then number 3 is dynamic routing. So in our case, we have to look at the AS path length. For the traffic to go via Transit Gateway A from region 1, there are 3 hops. Transit Gateway, Direct Connect Gateway, and your on-prem router, 3 ASNs. But to go from region B, it is 4 hops. So it will always take the region local route out, and if that fails, if Transit Gateway A fails, then it's going to prefer the route via Transit Gateway B. Let's induce failure. So our Direct Connect connections are down, both of them. Now, who thinks the traffic will be routed in this manner? Raise of hands. OK, few, very good, because that's not how it will be. So the traffic will be sent down to Transit Gateway because Transit Gateway A is still up and running. Direct Connect Gateway is a globally distributed, highly available router. Your Direct Connect connections go down, but Direct Connect Gateway does not. Now, this is an important one because you want to leverage Direct Connect Gateway's data plane to send hybrid traffic. You want to remove regional dependencies for any hybrid traffic. So you want to exit the traffic out of the region as soon as possible and hand it over to the Direct Connect infrastructure and let the Direct Connect Gateway handle the global routing to your nearest Direct Connect location. Now, this architecture by default does that, but not all architectures work that way. So I'll give you an example. Let's say we bring up a new AWS region. You provision VPCs, does not have Direct Connect connectivity. Traffic gets initiated. Now, the CNE in region 3 is equidistant to the CNEs in region 1 and 2. As I said, it's fully meshed. So it's going to send traffic to either Transit Gateway A or B. Let's say region 1 is US, region B is Europe, and region 3 is Mumbai, is India. You don't want your traffic to exit via your data centers in US, right? So what can you do about it? Well, it's quite simple. You create a Transit Gateway locally in the region, so you now have a local exit point. Hand over the traffic to Direct Connect Gateway locally within your Mumbai region, and then have Direct Connect Gateway routed to the nearest Direct Connect location. Now, another scenario where you have an egress segment to centralized internet egress. You have egress VPCs in US and Europe, but you don't have one in Mumbai. What's going to happen? The traffic is going to be sent to any of those regions, and it's going to be sent to US, for all you know. Now, you don't want that. So what do? Create an egress VPC in your local region, right? So try to always have regional exit points to avoid cross-region dependency. Now, if you do want to impose cross-regional dependency as purposefully, where you cannot create an egress VPC in the Mumbai region, there is a way to do it. We won't go into those details here because, again, you have to write static routes and create multiple segments and all of that. So definitely recommend checking out this blog. OK, so let's go back. My next requirement is to create SD-WAN connectivity to remote locations. You create your SD-WAN appliances in your VPC. You set up connect attachments, and you associate that attachments to a segment. And then you can create SD-WAN tunnels from your on-prem to these SD-WAN appliances over the internet. Of course, have multiple SD-WAN appliances for high availability. Pretty straightforward. Let's add another complication to it. We want to extend segments to on-premises. So in that case, let's start by looking how you do it with SD-WAN. So you would create 2 connect attachments. Here we are looking at the GRE connect attachments. And you would associate them with different segments. So I have prod and non-prod segments. So I create prod and non-prod connect attachments. And then I, in this case, terminate them on the same SD-WAN appliances, assuming that the SD-WAN appliance has VRF-like capability, where you can break your SD-WAN appliances in a logical manner into 2 isolated segments. One tunnel terminates on one VRF, other tunnel terminates on another VRF. And then you can extend that on-prem. Again, you can see a star mark in the bottom saying you have to use multiple appliances in different AZs for high availability. Now, what if your SD-WAN appliance does not support VRF-like setup? So you can just create or deploy multiple SD-WAN appliances and map individual SD-WAN appliance to a connect attachment, which then maps to an individual segment. Now let's look at scalability, because we are using Connect attachments. We already saw Connect attachments, have some limitations on how much bandwidth it supports. It's 5 gigabits per GRE tunnel. You can scale the tunnels, you can create more attachments, but again, the more you scale horizontally, the more operationally challenging it becomes. So you know where this is going, tunnel-less connect. So with tunnel-less connect, we create 2 tunnel-less connect attachments, associate those attachments to different segments, but there's a difference here. Let's bring back our architectural recommendations or considerations, sorry. You can only have 1 tunnel-less connect attachment per VPC, and the VPC attachment and tunnel-less connect attachment have to be associated with the same Cloud WAN segment. What that basically translates to is, for different segments, they should terminate on different EC2 instances in different VPCs. So that's how you would have to set this up. Now, if you had a large number of segments, then you will have to create, let's say you have 10 segments you want to extend on-prem. You'll have to create 10 VPCs. And for high availability, you end up creating 20 SD-WAN appliances, which might not be scalable. So you'll have to find a balance. If you have a large number of segments and your SD-WAN appliances support VRFs, then maybe going with GRE-based connect option might scale better for you from a cost and performance standpoint. Now, you can also extend segments on-prem over Direct Connect. For that, you have 2 options. One is on Transit Gateway, you can create connect attachments, associate them with Transit Gateway route tables, one with prod route table, one with non-prod table. Now, the prod and non-prod Transit Gateway route tables are associated with appropriate Cloud WAN segments, so prod and non-prod, and then you can basically extend that on-prem. On-prem, most routers support VRF configuration, so there'll be multiple tunnels terminating on different VRFs. You can scale by creating multiple GRE tunnels. The other option, obviously, is to create tunnel-less connect. Very similar to how we saw before, but now the on-prem to SD-WAN connectivity, instead of being over the internet, it will be using private IPs over Direct Connect. All right. So our final requirement is setting up dynamic routing between AWS Cloud WAN on-premises networks over Direct Connect. We have already done that. By creating these GRE tunnels and by setting up SD-WAN connectivity, we have automatically set up BGP peering between your Connect BGP peer and SD-WAN. So your on-premises routers or SD-WAN termination endpoints will exchange routes with your SD-WAN appliances in a dynamic manner, and then the SD-WAN appliance will exchange those routes with Cloud WAN in a dynamic manner. So you have end-to-end BGP if you go about creating an architecture like this. With this, you don't have to worry about the static routes configuration on Transit Gateway. All right. Now, I know you are waiting eagerly to hear from the Sonos speaker, pun intended. But before that, let's talk about some key takeaways. 10 things to remember. Number 1, it depends on your application's networking requirements. You need to focus on what your application needs and work backwards from that. Use well-architected framework. Building scalable networks doesn't really necessarily mean having the highest throughput. It also means being resilient. It also means being secure and cost optimized as well. Choose a default connectivity model and add other options as needed. As I said before, if you want global connectivity, I recommend using AWS Cloud WAN. But if you don't have any global presence, sure, you can go with AWS Transit Gateway as well. But these are the 2 options you have. And then bring in other options. VPC Lattice, we saw private link, we saw VPC peering. Understand what those offer and layer them on top of your default connectivity model. You should be building hub and spoke designs with centralized resources, right? So centralized NAT gateway, centralized security appliances. And then obviously we talked about handling exceptions like decentralized internet ingress. Net DevOps is a very important one. I'm sure many of you are already doing network automation, are using CloudFormation, CDK, Terraform. Strive towards pure net DevOps pipelines where you can also automatically test a lot of your networks. We have a bunch of tools, VPC Reachability Analyzer, Access Analyzer, whatnot, which you can embed into your CI/CD pipelines. There's generative AI now, so maybe you can use generative AI as well to do some of that testing. From an architectural standpoint, get the fundamentals right. VPC design and IP addressing. I cannot tell you how many customers I've interacted with whose scale challenges would have been solved if they have gotten this right. And they're now building landing zone 2.0, landing zone 3.0, I don't know, right? New design, which has a much better strategy around VPC and account setup. You can use shared VPCs, but keep in mind, you don't want to build really large VPCs. Keep track of the limits. We talked about how AWS Direct Connect data plane is different from what Cloud WAN is, and how you want to use Direct Connect gateway to send traffic globally for hybrid traffic and avoid any regional dependencies. Finally, we also saw the new announcement, the new feature, Tunnel-less Connect, which is now the recommended approach for SD-WAN connectivity. And finally, with AWS Cloud WAN, we also saw how route priority works. When you're building really large scalable networks, you will have scenarios where you will have suboptimal routing, and you will have to come back to this route priority design and redesign things in a way so that you can get optimal routing. With that, Ben, all yours.
Thanks, Sid. Hi, everyone. Thanks. In business for over 2 decades and with thousands of patents, Sonos strives to deliver category-leading sound experiences. Oops, sorry. So I want to tell you a little bit about our network journey with Cloud WAN, and I'm here because I believe all of these products that Sid just mentioned, everybody should use them because they provide more capacity, it's cost-effective, and there's a lot of security benefits. But let me just tell you, most of Sonos' journey was on-prem, no cloud. So we started with a little bit of hybrid, a couple VPCs, a couple accounts, site-to-site VPN connections. And that didn't really scale well once we started adding more and more VPCs. So we needed something that was a more advanced solution. And that was Transit VPC. I don't know if anybody, show of hands, does anybody remember Transit VPC? It's not bad. So we deployed that, and in a couple of years, Transit Gateway came out. We didn't dive right in because we really liked the dynamic routing capabilities of Transit VPC. And so we worked with our AWS account team and gave feedback, and we eventually did migrate away, but to Cloud WAN. What made Transit VPC so great? It's global. It was a customer-managed construct with appliances in your Transit VPCs, hub and spoke. Spoke VPCs is where the applications would live. But really, it had some scale issues, of course, but we were able to get some more life out of it by working around some of the capacity issues, stitching up VPC peering connections. We built a custom automation pipeline to deploy the Transit VPC infrastructure in multiple regions. And when we wanted to add more regions, we'd have to replicate that. And then there's also a licensing and support model to manage. So in 2022, we were psyched. AWS Cloud WAN. We'd waited long enough, so we're glad. It connects everything and then some for us. It's great. We needed a global network solution that could deliver, hundreds of or connect hundreds of VPCs, deliver, intra-region capacity that we wouldn't exceed, cross-region bandwidth limits that we wouldn't exceed. Of course, it was cost-effective, and I'll just skip the operational and automation things for a moment. But the resource sharing part is really great because you use AWS's Resource Access Manager to share your Cloud WAN core networks with other accounts, and you can do that at the organization level or at the account level. This lets the DevOps teams responsible for those accounts connect whatever VPCs they need to, as needed, without any intervention from the network team. All right. So in terms of automation with Cloud WAN, we really benefited from shifting responsibility to AWS. I think I might have just mixed one. Oh, yes, I didn't say that. Oh, absolutely, there it is. The core network policies, the JSON document that you saw earlier, that replaced a ton of our automation. So we shifted a whole bunch of that just by going to Cloud WAN. One of my favorite parts is the attachment policies. That allows the DevOps teams to set various tags on the attachments, and then the attachments get placed in the appropriate segments based on the attachment policy rules that are embedded in that network policy. In terms of interoperability, yeah, the old solution that we'd had, we loved it because it was link state routing protocols, and we used internal BGP. But now with Cloud WAN, we use eBGP and ECMP. In terms of connecting to all the things, yeah, we connect our SD-WAN stuff to it, connect our other clouds. But one of the pluses to making this jump is that AWS just listens to customer feedback and gave us, it seemed like they gave us what we were asking for, but I bet a bunch of other people were asking for it as well. But yeah, and I'm really thankful. The people that make these products are working really hard behind the scenes, so I'm appreciative. It's like having your own private MPLS network, and then they maintain it and patch it, and they even improve it. When we first started using this, it was 50 gig per second per attachment, and then without even saying anything or turn around, it's 100 gig per attachment per AC. It's great. And with that more capacity comes more flexibility. And for us, that's something like centralized NAT, egress. We could build our network and pay, globally and pay for what we use. And then, of course, there's security benefits. The VPC isolation, or the VPC attachment isolation, and segment or macro segmentation capabilities, as well as inspection architectures that come along with this solution are great. So what's next for us? After we sort of switched to Cloud WAN and we're happy, we keep expanding. The new service integrations that I'm sure we'll hear about at some point, we're expecting they'll be just as easy to use as Cloud WAN is now. And then also we're going to peel away some of our GRE tunnels and replace them with these tunnel-less connect peers. So, oh no, whoops. For a little more information, please check out our case study, and you can get the code there. And I guess with that, I'd say I hope this was helpful for you. It's definitely helpful for me, Sid. Thank you.
Yeah. Thanks for being here and sharing your story. So we also have this networking core digital badge and learning pathway. So if you want to get started with some free resources and learn about Cloud WAN and a lot of other networking services, you can get that and you get a verified digital badge as well. Thank you so much. Please complete the survey. My colleague Ben here, or my friend Ben here would love 5 stars, not me. We ended earlier than I anticipated, so I think we can take some questions.